Analyzing graphs of polynomial functions. So in this chapter section, we're going to be looking at several characteristics of polynomial functions given the function itself. And in this first example here, it asks you to graph a polynomial function making a table of values. And I'm actually not going to do that, but if I did, I'd have x and y, or let's say f of x equals 1y. And then you would substitute values in for x and determine what the dependent variable is, or the y or f of x is, for that value of x. And you'd plot those points on a coordinate plane, and then you would begin to connect those dots. But really importantly, there's several things, and I'll just discuss just a few of them, not all of them, that we can tell from this equation itself. First, it's x to the fourth. That exponent is even. That means that the end behavior is going to be going in the same direction. And then since that is positive, then end behavior both on the right end and the left end are going to be out towards infinity. Also, it tells me that it's possible, but not guaranteed, that there could be 4 real zeros for that polynomial function. In other words, that the graph would cross the x-axis, could be as many as 4 times. There will be 3 turning points. We'll see typically an x to the fourth, not necessarily with all this transformation going on, will look something like a w. And you could have as many as 3 turning points. A lot of times on a graph, particularly on a graphing calculator, some of those turns may be so subtle that you really can't even recognize them. What else? Oh, I got a y-intercept at -6, so we should cross the y-axis at -6. There'll be at least one relative maximum. There'll be a couple of minimums, or could be a couple of minimums, will be a couple of minimums. One may be relative, one may be absolute. Anyway, what we are going to do, though, is we are going to graph this on a calculator, and we're going to look at the table of values. In fact, this and the next exercise as well. And we'll look at the graph. So let's head to the graphing calculator, and let's graph this x to the fourth minus x cubed minus 2x squared plus 4x minus 6. All right, here we are on our calculator, and we're going to graph this function. And it starts off with x to the 4. So I hit x and the little caret button, in case you don't know how to do that, and 4. Then move the cursor over. And let's see, it was minus x cubed, so minus x caret 3. And then negative 2x squared, so minus 2x squared plus 4x. And then minus 6. All right, well, let's go take a peek at the graph. Okay. Well, you can see that my end behavior, both left and right, are headed out towards infinity. And there's one turn. There's two. There's probably one right in there. But it's very subtle. I'd have to get this table. I'd have to change the scale on this thing quite a bit probably to be able to see it show up on the calculator. And I'm crossing the x-axis in 2 places. Remember, I said it was possible but not guaranteed that we'd have 2 real zeros, which is telling me that we've probably got 2 complex zeros, and complex zeros are always going to come in pairs, so that would make sense. 2 imaginary zeros, if you will. But let's go look at the table right quick. So we hit second graph, and I can see here when x is -3, y is 72. When x is -1, y is -10. When x is 2, y is 2. Got a little bit of symmetry right there. When x is, look how about when x is 7. y is 1,982. Let's go back now in the direction, negative direction a little bit. See what happens. Well, we got negative 7. What's happening when we're at negative 7? Y is 2,612. So we got some pretty large numbers in there. Now, in the next video, we're going to be looking at the table of values, and we're going to be talking about something called the location principle, whereby from the table itself, we can determine about where, but not maybe exactly where, this graph is going to cross the x-axis. Be ready.